All right, now let's take a look at question 2.2, which asks, what's the depth of a quantum volume circuit of 5 qubits and a depth of 5 after decomposition into the basis gates U3, CX? And as we discussed in previous videos, the U3 gate has been deprecated and replaced by the U gate in Qiskit. But as we will see, this quantum volume circuit is still being implemented using U3 gates. That's probably something that needs to be fixed within Qiskit, but really it doesn't make a difference since the U gate is the same as the U3 gate. Okay, so I don't want to spend too much time talking about what quantum volume is in this video, because later in the exam there's another problem in which we are tasked to measure the quantum volume of a specific circuit. But I do want to just discuss a little bit of the basics and what this quantum volume function, which is actually a circuit that is incorporated within Qiskit's circuit library. I want to discuss what this is. So okay, so let's do question 2.2. And first, I just want to say that quantum volume of QB is a single number metric. So it's a single value that we use to quantify or to benchmark how well a quantum processing unit, or a QPU, how well a QPU performs, or how it compares to other quantum processing units, and this metric captures a few things. So it captures in general the total number of qubits. It also gives us a way to measure how good of a connectivity our QPU has, so connectivity between qubits, which is a function of the topology of the processor, and also the number of gates, which is usually referred as the depth of the circuit, that can be applied before the errors of the hardware affect this metric. So we're not going to discuss what this metric is, how it's calculated, but one important thing is that the way quantum volume is measured is by using a specific type of circuit, which consists of randomly generated and randomly connected gates. And more specifically, these are 2 qubit gates, and they're generic in the sense that they can express any type of rotations in 2 qubits. So the circuit in general is implemented using a set of, for some reason they label this with a pi, but what this block represents is permutations between qubits, followed by this SU4 unitaries, or SU4 blocks. So we have here a few SU4 blocks, and I'll explain in a second what these are. But what's important here is that this corresponds to one layer of this quantum volume circuit, and then this is repeated many times. Specifically, let's say this is the second layer, and then this is the def layer, and then this is for a total of let's say n qubits. So the way quantum volume is measured is by first applying this circuit to quantum hardware for, let's say, 1 qubit and 1 layer, then it's increased to 2 qubits with 2 layers, and so on and so forth, until when this metric, this quantum volume is measured at the output, doesn't meet a certain criteria. And more specifically, this block right here is just permutations between this qubits. So if we have, for example, 4 qubits here, this gate could be just, let's say, a swap gate between qubit 0 and qubit 4, and then a swap gate between qubit 1 and qubit 2, or it could be this is selected randomly, how these permutations happen, and the circuits are run over and over again and then averaged out. But this can also be like a swap gate between qubit 0 and 1, and then 2 and 3, and so on. And for more qubits, you will have more permutations. And this SU4 is basically a general rotation for 2 qubits. So it's implemented using U gates, and then entangled with CNOT gates. And to generate this very general circuit, this is actually repeated 3 times, so 3x, this same circuit. Okay, so this is a very brief explanation of what this circuit entails. So now let's go back to our question and see what we're being asked. So we're asked, what's the depth of this circuit? So let's go ahead and from Qiskit and then circuit library, let's import this block quantum volume. Okay, and then let's generate our circuit. Let's just call it, for example, QC equals quantum volume, and let's specify num qubits equal to 5 and depth equal to 5. And then let's do here, let's just draw our circuit. Let's draw our circuit by doing qc.draw. And as you can see here, well, we're just generating this block that has circuits inside. So if we want to see what's going on inside, what we can do is do qc decompose dot draw, and then that shows us that we have this SU4, this 2 qubit unitary. So in this case, this is being applied between qubit 1 and qubit 0, this one between qubit 2 and qubit 4, qubit 1 and qubit 2, and so on and so forth. Now you might say, well, this looks a little bit different than one we had before. Well, it's actually the same. The difference is that before, instead of going ahead and applying these qubits or these gates directly between adjacent qubits, and swapping, using swap gates to change which qubit is applied to each of these SU4s, here we're just directly applying them to different locations. Now, if you want to get something closer to what we described a minute ago, what you can do is here you can specify classical permutation, and then we can set that to false. So that means that instead of applying these gates classically between these 2 qubits, we actually implement the permutation using quantum gates. And then if you see here now, this SU blocks are only applied between adjacent qubits, and then this permutation block, if we decompose it one more time, you'll see that inside it'll have this permutation gates or the swap gates. So let's give this a minute, and then you can see here there are the swap gates, and then these are the SU4 blocks that I described before, which are usually in blocks of three C0 gates. So let's just turn this off or remove that again, and then just generate this circuit without the quantum swap gates. And what we're asked here is, okay, well, what's the depth of this circuit once we decompose it? So let's go ahead and actually save this in a separate circuit. Let's do QC decomposed, and let's just save it like this. And then what we can do here is we can use this depth method. So we can do QC decomposed dot depth, and then it'll give us the depth of the circuit, which is 35, which means that our answer is 4. So if we go back here and let's just draw the circuit one more time, we could try to count the number of layers there, and let's actually do here fold -1, and see that if we were to count this, there will be 35 layers of gates, one after another.